Welcome everyone. Today we are going to start a new chapter, that is electromagnetic induction. To start electromagnetic induction, one basic thing we're supposed to know is magnetic flux. So the definition of magnetic flux is similar to the definition of electric field. So suppose we have a plane surface in uniform magnetic field. So here 6 number of magnetic field lines are there and only 4 magnetic field lines are crossing through this surface. So the number of magnetic field lines which are crossing through this plane surface are called flux. So here the value of flux is 4. Mathematically, this formula is flux is equal to dot product of magnetic field and surface area, and in scalar form BA cos theta. Theta is the angle between magnetic field and area. So there are two cases. If theta is 0, it means magnetic field is perpendicular to the plane of surface. And we all know that the direction of area is also perpendicular to the plane of surface. So that's why the angle between B and A is 0 and phi becomes BA because cos 0 is 1. So if the theta is 90, then magnetic flux is 0. So as you know that this dot product of two vector quantity is always a scalar, that's why magnetic flux is a scalar quantity. And what about its SI unit? The SI unit of magnetic field is Tesla and SI unit of area is meter square, so it becomes Weber. So SI unit of magnetic flux is Weber. But how to calculate the dimensional formula of magnetic flux? To calculate the dimensional formula, we have to know the dimensional formula of B. So there is a relation in which B is involved, magnetic field is. So write the dimensional formula of all the terms. Dimensional formula of F is MLT minus 2, for Q it is AD, for V LT minus 1. Keep B as it is because we are supposed to find the dimensional formula of B. So here T and T inverse cancel out, L cancel out. So there is M T minus 2 A inverse. This is the dimensional formula of magnetic field, and for phi we have to multiply it with the dimensional formula of area with L square. So it becomes ML2, right? Dimensional formula of area L square and T minus 2 A inverse. This is the dimensional formula of magnetic flux. Now if we want to calculate the magnetic flux for irregular surface, this is a regular surface. For irregular surface, how to calculate it? So suppose this is an irregular surface. Now we divide this irregular surface in small surface areas like ds. We divide this irregular surface into small surface areas. So magnetic flux linked with the small surface area is, this is the B, direction of B, and this is the direction of area, and theta is tangent to theta. Right? So the small magnetic flux linked with the small area is d phi is equal to ds. This d phi is the magnetic flux linked with this small surface element, surface area. So now there is a number of surface area, small surface area. So to find the total magnetic flux, we have to add all this, and to add all this, we have to integrate. So integration of BDS, right? So this is the total magnetic flux for irregular surface. Now coming on to understand electromagnetic induction. To understand electromagnetic induction, we have to know about the Faraday's experiment, because Faraday's experiment led to the discovery of this phenomenon, electromagnetic induction. So in this experiment, there is a coil which is connected to the galvanometer. This galvanometer is here to check the presence of current, whether the current is flowing in this coil or not. So in this experiment, in the first step, when the magnet is stationary, when this magnet is stationary, then there is no current in the coil, right? And when this magnet is moved towards the coil, then there is production of current, which is observed through this galvanometer. Galvanometer shows deflection there. And in third step, stop magnet near the coil. We just stop the magnet near the coil, then there is no current. And in the fourth step, moving back, we just move this magnet away from the coil. Now there is a current, but it is in opposite direction. In fifth step, stop magnet anywhere. We stop magnet anywhere, then there is no current. So from this experiment, what we observe, when the magnet is stationary, then there is no current in this coil, right? And when the magnet is moving, then there is a current. In both cases, whether magnet is moving towards the coil or it is moving away from the coil, right? When the magnet is away from the coil, then few magnetic field lines are linked with this coil. So at this time, the value of magnetic flux is 2. When the magnet is moving towards the coil, then more number of magnetic field lines are linked with this coil. And now the value of magnetic flux increases. So in this way, the magnetic flux is changing when the magnet is moving towards the coil, and value of magnetic flux also changes at the time when the magnet is moving away from the coil. So we can say that when the magnet is moving, then there is change in magnetic flux. This leads to the production of induced current. And this process is called electromagnetic induction. And this is the Faraday's first law. Whenever there is change in magnetic flux linked with the coil, then there is induced EMF is produced, right? And in the Faraday's second law, he gave the magnitude of induced current, that how much induced EMF or induced current is produced. So magnitude of induced EMF is directly proportional to the rate of change of magnetic flux.